Good day, everybody. In this short lecture, we want to see how in Delft 3D we can simulate models using different sediment fractions or graded sediments. First, the overview of what we will hear in this afternoon. First, I will just briefly explain why sediment mixtures are important for river and coastal engineering. Then I'll explain the formulation implemented in Delft 3D and how this formulation is validated using flumes and experiments, and maybe one example of application, and we will do some exercises together. First, why is it important to model the sediment mixtures? Just think about river bifurcations. When we have such a system, then there is a selective distribution of the sediment transport and sediment size downstream. And that will change the morphological behavior of the whole system depending on the amount of the fine or coarse sediment that moves there. Or if we have rivers which are navigable and there are shippings happening there, the estimation of bed forms are very important because those bed forms can locally reduce the available depth of the river for shipping and cause problems. And the formation of those bed forms are a function of the type and size of the sediment that we have. Other reasons to look into these sediment fractions is in reservoirs of dams. Because first, it is important for the dam operators to see what type of sediment comes to the reservoirs and where they are deposited. And if there is a project to restrict the dam or remove the dam, what type of sediment from the basin will go downstream in the river and eventually to the coast. So it is important to know the location of the deposition of different sediments in the reservoirs. Or if you want to, for example, do a flushing of a reservoir, you need to know where in the reservoir your fine or coarse sediments are. For example, in a study that we did in a reservoir in Sudan, you can see a cross-section of the basin here, and you can see that the sedimentation in this area, we could see how much coarse or fine sediment have been deposited here during years of operation. By the way, this is done by Delft 3D. Or in other cases that the sediment mixture is important is a long-term morphological behavior of estuaries in coastal zones and also other bays. For example, in this study that we have done for San Pablo Bay in the United States, we have shown that if we don't consider the mixture of sediment and different type of sediment in our simulations and compare it with the simulations which included different fractions of the sediment, the results are very different. And the one with sediment mixtures are closer to the reality. The comparison here is shown in this figure A and B. A is for uniform distribution of sediment, and B is with using an actual distribution of different fractions. And you can see that there are considerable differences there. Maybe good to repeat that Delft 3D can do 2D or 3D hydrodynamics with sediment transport and morphology, and also you can impose wave models, water quality, and ecology on top of it. But now we are focusing on the sediment transport. In Delft 3D, we can use many different type of sediment transport relations. For example, we can look at the Mager-Peter-Muller, England-Hansen, Ashida formulations, or we can, if suspended load is more important for us, then we can look at the Van Rijn formulations. And if there are quite a bit of mud involved in this model, in our case, then maybe we need to also use the Niades and Cron formulation for that. So all these are possible to use in Delft 3D. And the arbitrary number of sediment fractions, practically up to 99 different sediment fractions and sediment types, are possible to be used in Delft 3D as well. One of the things that is interesting to think about when you're talking about sediment transport formulations with graded sediments or with different sediment fractions is the hiding and exposure effects. This is the main cause of something like armoring, for example, because when you have two types of sediment, imagine fine and coarse sediment, after a while when they mix and fine sediments start to moving and being eroded by water and by water movement and current, then on top of our bed there are usually more coarse sediment remaining, and sometimes they start protecting what is underneath. So practically some fine sediment, and that is it's called the armoring of the bed or hidden exposure effect. This is also included in the Delft 3D simulations. The other important part that we have in the 3D sediment transport formulation is bed load transport formulation and the effect of secondary flows and streamwise and transverse bed slope effect. Most probably you have heard about these in the previous lectures, but just to have a complete lecture, I am putting it here. So when there is a secondary flow, usually you have other forces on the sediment as well. Because we are making a 2D model, depth average, resolving the secondary flows in a 2D average model is not easy. So there are some empirical ways to add these to that add these effects to the sediment transport, and it is included in Delft 3D if you turn that on. But it cannot be used for sediment transport formulation of Biker, Soulsby, Fundry 1983 and 2004. The other two important parameters are the bed slope effects. When a grain of sediment is on the slope, then beside the current, its own weight also influences the amount of movement. Uh, Usually using the empirical sediment transport relations, we calculate only the sediment transport, assuming that it's on a flat bed. But to include the effect of these slopes, Delft 3D adds two sort of multiplications or coefficients to the sediment transport. One along the canal, and the other one is in the transverse direction of the canal. So for example, if we can calculate the sediment transport S using our empirical sediment transport formulation, for example, England, Hansen, or Van Rijn, or others, then there is an additional component because of the slope in the direction of the flow. We call it S prime, and additional transport perpendicular to those initial transport, which is due to the transfer bed slope. The formulation are in this slide, and if you are interested in it, you can look into more details in the manual. The other issue, which is the main focus of this lecture and exercises of this lecture, is bed composition model. Bed composition model look into actually the composition of the bed materials under a riverbed or under a seabed. What is currently implemented is based on Hirano model, which has a transport or active layer. It is extended to 2 layers, and it has also passive bookkeeping layers, and it can work with arbitrary number of fractions of sediment. So 1 to almost 99 different fraction of sediment that can be sand, gravel, or mud. Uh, Usually in a river application, we can use up to 20 bed load fractions. And in coast, we have used like to 5, 6 different fractions based on the data that we have. But how does this model works? Imagine that we have a column of water and soil, So water, of course, is what we use the hydrodynamic model to calculate that. And underneath the water, inside the soil column, we can either have constant sediment, for example, in this case, a mixture of 50% sediment 1 and 50% sediment 2. It is homogeneous and similar in the whole depth of available sediment, which is this. Or we can have actual physical layers. For example, in this case, in this layer, we have 100% of sediment 1, 0% of sediment 2. In this layer, we have 90% of sediment 2, 10% of sediment 1, and underneath is 50-50. Now, we want to use these examples for a while. We assume that S1 is a finer sediment and S2 is coarser sediment. Then, in the numerical modeling of this bed composition, we have an active layer or transport layer. You can see the one which I produce here with a thick box. We call this an active layer. Active layer is always present, and this is the layer that communicates with the water. So the water, the sediment which is eroded from the bed goes from this layer to water. And if there is a deposition and sediment wants to come from the water column to bed, it enters this sediment layer, so this active layer. Again, these are for two cases, one homogeneous mix and another one with different physical layers. Underneath that, we will have bookkeeping layers. So these ones which I have with dash and dot points, these are bookkeeping layers. These are only the layers that we can later visualize the changes of the sediment composition in these layers. So it is like making a grid, but inside the bed. The bookkeeping layers, the maximum number of that is indicated by the user, and it can be between 0 and as many as layer that we want. Under whatever remains from the available sediment is called base layer. That is also always present, and everything that does not fit into active layer and bookkeeping layer will be called base layer. But be careful that these active layer and under layers are numerical layers, so they don't have necessarily different physical characteristics. They can have, but not necessarily. This is only a bookkeeping numerical layer. At the beginning of the simulation, so initial step, active layer gets sediment from initial bed. It can be one or more underlayers. In this case, it is one underlayer, all the sediment in the active layer. Then the thickness of active layer is constant in time, and we should choose it as a proportion of the water depth. So again, now we have in this case one active layer and one bookkeeping layer, and underneath there is a base layer. If we are talking about the erosion, then the sediment is eroded from active layer and goes into the water. And the maximum erosion in one time step is the amount of sediment which is available in this active layer. But if we have in deposition mode, then the sediment comes from the water column into the active layer and deposits there. And the net, you can have different fraction of sediments, of course, mixed into this active layer, and the net effect is sum of fractions. If the net effect is that we have erosion, then the active layer gets sediment from the bookkeeping layer underneath. And if the net effect is deposition, then the sediment is removed from the underlayer. Underlayer moves up. So the active layer moves up, and then we will have new underlayers generated. Yeah. So this active layer can have more than one fraction of sediment, which is mixed with a specific percentage in this active layer. So now if we want to look in sort of a cartoon of what happens, we can look at it here. This is now an erosion condition. So initially, we have an active layer, we have two underlayers, and we have base layer. And this is the time. So then and imagine that we have two fractions of sediment, one fine and one coarse, which is mixed 50% with 50% there. When the erosion starts, usually the finer sediment first goes out. And because the fine sediment goes out and some sediment is coming into the active layer from beneath, the overall new active layer is getting coarser and coarser and coarser and coarser because fine sediments moves to the column to the water column and goes away. And then the erosion happens and bed level goes down and down. And you can see that the active layer is eating into the underlayers. Now, in this case, is a bit different. We have three different fractions. And then you can see that the active layer moves in, moves down, gets a bit coarser, but as soon as it gets to a new physical layer, it may even get very coarse because this new material may be very, very different. If we have a sedimentation or deposition, it's the other way around. So usually the coarser sediment falls faster. Yeah. And after that, the finer sediment may come. But when the sediment comes from the water column to the bed, especially first, the active layer is growing to become the thickness that we have given to the model. And after that, the underlayers are becoming more and more visible. And depending on the type and amount of sediment that are deposited, the active layer and underlayers may differ. So these are the principle of how this bed composition model works. If you are using the dredging option of Delft 3D and you want to model the dredging, you should be aware that dredging always remove the top layer, whatever it is. Yeah. So doesn't matter what's the mixture of the top layer. It just take that part out, and then the active layer will start in the next step from beneath the new bed level after dredging. And it is also interesting to know that when we are talking about this bed composition model, they may have completely different characteristics. So there may be physical layers underneath the bed. And when you have more depositions, in reality, some compaction also happens. Yeah? And this compaction is not taken care of for in the normal version of Delft 3D, but there are some Delft 3D models that take care of this compaction, which you can find them if you want to do some research, which this compaction is very important. You can ask for those type of versions of Delft 3D from Deltaris. So this is more or less an example of a simulation, and you can see that we have base layer, we have multiple bookkeeping layer, and we have active layer. And this and this is the shape of the bathymetry at the time of this picture. And each of these bookkeeping layers may have different percentage of different sediment fractions mixed there. When you do the exercises, you will see better results and you will understand it most probably a bit better. There have been validation. So using this model, for example, this is the validation of the Riberink 87. The solid lines and dashed line is the result of the models, and this circles are the measurements. So they were close to each other, and there were also validation done using curved volume, using 50% fine sediment and 50% coarse sediment. And then they looked at the measurement and the result of the model, which are pretty okay. And in this validation case, they also looked into the changes in the bed level elevation, because now we have a spiral flow as well, and then the bed level changes may be different in the inner bend and outer bend, and also the the sediment transport for fine sediment and coarse sediment also are pretty different because of the shape of this curved flow. And you can also see this in these two slides. Now we are looking at the fine sediment transport, and here we are looking at the coarse sediment transport, which happens more on the outer bend. And then the grain size distribution happens here. You can see that the coarse sediment are going more towards the outer part of the flume, and the fine sediments more towards the center of the flume. You can also see some application of these models. It was applied to a bifurcation of a river, so relatively coarse sediment were going towards the north branch and finer sediment towards the southern branch. So this was an application that these type of models have been used. As some final comments, I should say that the state of art modeling allow for an in-depth analysis of the physical processes interacting in modern day rivers. These models can also provide valuable data on the deposits left behind by various morphological events. But be careful that when we are making our models more complicated, it means that also we need to have more data. And the data, especially for underbed or what is lying underneath the bed surface, are usually not available. Yeah. So it is nice to be able to visualize them and everything, but to calibrate those models or even compare it to reality a bit to validate the model, those data does not exist in almost all around the world. Yeah, so you should be careful if making use of these complex models is beneficial for you and you can compare it with reality, or you have enough data to make your initial condition or not. Okay, thank you for listening to this lecture. Now you can go and look at the videos for exercises and try to set up a model using bed composition model.